right, okay, so last week we discussed some basic definitions and properties about graphs. Okay, so we consider the relationship between the minimum degree and the connectivity of a graph. So for example, we prove that if the minimum degree is m minus 1, then the graph is connected. And then we also lower this threshold and prove that if the minimum degree is at least n over 2, then the graph is still connected. Okay, so yeah, that's two properties that we discussed last week. And also we consider the problem of degree sequence. Right, so given a degree sequence, we would like to know whether there's a graph that matches this degree sequence. All right. So for example, like this one, 3, 3, 2, 2, 1, 1. So this degree sequence can be realized by a graph. By that I mean that we can find a graph that matches this degree sequence. Okay, so the graph looks like this, right? Okay, so for this graph, the degree sequence is 3, 3, 2, 2, 1, 1. Okay, and by the way, the graph that realizes the degree sequence may not be unique, which means you can find different graphs, but they all matches the degree sequence. Okay. Okay, and some degree sequence is not cannot be realized by a graph. Okay, and by the way, we said that if a degree sequence can be realized by a graph, or you can find a graph that matches the degree sequence, then we will call the degree sequence graphical. Okay, so so this degree sequence on the right is graphical. However, this one 3, 3, 3, 1 is not graphical because you cannot find a graph that matches or realizes this degree sequence. So this one is not graphical. All right. Okay. So the problem we considered last week is that given a degree sequence, we have to determine whether this degree sequence is graphical or not. All right. And we have a very simple simple algorithm for this question. So because if the degree sequence is graphical, then it will mean we can find a graph, or we can construct a graph that realizes the degree sequence. So in our algorithm, we really try to construct a graph that matches or realizes the degree sequence. So the first step is to create vertices. Okay, and so we're going to assume that the number of degrees, or the length of the degree sequence is n, which means we need to create n vertices. So this is the first step. Okay, just create vertices, and then we have this target degree, or the remaining degrees you have to add to satisfy the degree sequence. So to add edges or to satisfy these target degrees, like this one, okay, 3, 3, 2, 2, 1, 1, we have to add edges. Okay, so the way we add edges is to, well, first we're going to pick a vertex. Okay, actually we can pick any vertex we want. Okay, say we pick V1, all right, and then we have to add edges to this vertex. Okay, the vertex that we choose in step 2. Okay, so we're going to choose the neighbors based on the, first of all, the number of its degree, the target degree. So in this case, the target degree is 3. So we're going to choose 3 neighbors. All right. So now the question becomes, which 3 neighbors should be chosen? So our basic idea last week is to choose the one that has the highest target degrees. Right. So in this example, if we want to choose 3 neighbors for V1, we're going to choose these 3 because they have the largest target degrees. All right. So we're going to connect V1 and V2, all right, and then V1 and V3 and V1 and V4. All right. So this finishes a round, and then we're going to repeat this process, okay, until all the target degrees become 0. Right. And last week we also considered like a variant of this algorithm where we change the design for the step 3. All right. So in this step, originally we choose the one that has the highest degrees, but then we consider another variant that we choose the lowest target degrees. Okay. So for example, in this case, suppose we choose V1 in the second step. Then in step 3, we're going to choose V4, V5, and V6 because they have like the lowest target degrees. All right. And it turns out that this algorithm is wrong in the sense that this degree sequence is graphical. However, the algorithm cannot give you a graph that realizes this degree sequence. Okay. So today, our first goal is to prove indeed the first algorithm, that is, if we always choose the vertices with the highest target degrees as the neighbors for the vertex that we choose in step 2, then the algorithm will be correct. By correct, I mean if the degree sequence is graphical, then this algorithm can really output a graph that realizes the degree sequence. And if the degree sequence is not graphical, then it will output not graphical. Okay? Right, so that's our first goal today. Okay, so before I start, are there any questions regarding the algorithm that we discussed last week? 有问题吗？就是关于我们上礼拜讨论的内容，因为我们等一下要做的事情就是要去看刚刚的第一个演算法，看它为什么是正确的。所以第一个演算法蛮单纯，就是每一个回合都选一个 vertex， 随便选一个，然后在帮他选 neighbor 的时候，都会选那些 degree 最大的那些。Okay. All right, so to prove that the algorithm is correct, we're going to need some notations. Okay. So first of all, I'm going to that. Sorry. So we're going to that D be the input degree sequence. Okay, so this is our input. Furthermore, we're going to assume that D1 is the largest degree, okay? And D2 is the second largest degree, and so on. So Dn will be the smallest degree. Okay, so this is our input. All right. So observe that in our algorithm, that is, we consider the correct one, okay? We actually modify this degree sequence, okay, in every round, because in every round, we're going to choose a vertex, and we're going to, for example, in this case, we're going to add 3 edges to V1. So we're going to sort of like change this 3 to 0, because now the target degree becomes 0, since we have added 3 neighbors. So now the degree becomes 0. And then we're going to add edges between V1 and V2, and add edges between V1 and V3, and V1 and V4, okay? So this means we're going to subtract 1 from 3, 2, and 2. So now these degrees become 2, 1, and 1, okay? So we're going to update the degree sequence. Right? So after a round, the degree sequence becomes So I'm going to use d prime to denote the new degree sequence. And also I'm going to assume, just for the sake of convenience, in step 2, we choose the one that has the smallest degree, okay? But in fact, you can choose any vertex you want, okay? To make our life easier, we're going to assume that this one has the smallest degree. Okay. All right, so if in step 2, we choose the smallest degree, which means that after a round, dn will become 0 because we have fulfilled all its target degrees. So you want dn neighbors, fine, I'm going to give you dn neighbors. So dn will become 0. Okay. And step 3 is still the same. We're going to choose the one that has the largest degrees. So these degrees, okay, D1, D2, and D3, and so on, they will be decreased by 1 because we're going to assume that we add an edge between D1 and Dn. Okay. And let's further assume that Dn is delta, right? So this means we're going to modify delta degrees because all the first delta degrees will be decreased by 1. Okay. Okay. So the reason that we have this -1 for these degrees is because we add edges between these vertices and Vn. Okay. So the remaining degrees are not changed. All right, so this D prime will be our new degree sequence. Okay, so let me give you an example. Okay. All right, so let's use this degree sequence as an example. So D will be 3, 3, 2, 2, 1, 1. Okay. And what is D prime? Okay. So in our first round, we're going to choose the one that has the smallest degree, that is V6. Okay. So we're going to find V6 one neighbor, and that neighbor will be the one that has the largest degree, which will be V1. Okay. Okay, so as a result, the degree for V1 becomes 2, and the degree for V6 becomes 0. So our new degree sequence will be 2, 3, 2, 2, 1, 0. Okay. So that's our new degree sequence. Okay. So in order to prove that our algorithm is correct, what we have to do is to prove that this D prime it has the same answer as D. So what I mean by this is that if D is graphical, then D prime is graphical. And if D is not graphical, then D prime is not graphical. So that they have like the same answer. Whether if the first one is graphical, then the second one is also graphical. And if the first one is not graphical, then the second one is not graphical. So if we have this property, then we can prove that the algorithm is correct, because we're going to keep reducing this degree sequence until it is so small that we can see that the algorithm is correct. Right. So our goal is prove that D is graphical if and only if D prime is graphical. So before I continue, let's go back to the previous wrong algorithm and see what is the D prime for the wrong algorithm. Okay. Oh. Okay, so in the wrong algorithm, when we pick V1 in the second step, we're going to find V4, V5, and V6 as the neighbors for V1. So what is D prime? So D prime becomes 0, 3, 2, 1, 0, and 0. Okay. So this one is D, and this is D prime. Okay. So D is just the input degree sequence, and D prime is the degree sequence after the first round. Okay, after we add some edges to the graph. Okay. So we all know that D is graphical, but the problem for this algorithm is that D prime is not graphical. Okay. So the first one is graphical. However, for D prime, it is not graphical. Okay, so this is why the algorithm is wrong, because from in the first round, it transform a graphical degree sequence into a non-graphical degree sequence. Okay, so the answer will be wrong. Okay, and I think it's easy to see that this one is not graphical, because for this degree sequence, it has 3 vertices of no neighbors. Okay, so these three vertices are like isolated. Okay, so actually we call this degree 0 vertices the isolated vertices. Okay, so we have 3 isolated vertices, and for the remaining 3, their degrees can be at most 2. Okay, so these 3 vertices, they have some neighbors. Okay, but since there are only 3 of them, the maximum degree can only be 2. Okay, so you cannot have a degree 3 here. Right. So if you have a degree 3 here, this means you have, other than this one, you should have at least 3 vertices of degree higher than 0. Okay, so this one cannot be graphical. Okay, 所以我刚刚说的事情是，在刚刚我们前面看的这个上礼拜看的这个错误的演算法里面，它之所以会出错，就是因为它 D 跟 D prime 是他们有 不一样的答案。我所谓不一样的答案就是本来的是 graphical，OK 啊，但是你转换之后它变成不是 graphical，所以你的答案就会出错。像这个例子来讲的话，它的就会变032100，这个就不会是 graphical，OK，因为你最大 degree 是3的话，你至少要有除了它之外要有3个点，它的 degree 要大于0，OK，所以这个很明显不是 graphical。有问题吗？到这边为止。有吗 ？Okay, so so next we're going to prove this. Okay, so this statement has 2 directions. Okay, so the first direction is to show that if the input, that is D, okay, if the input degree sequence is graphical, then the new degree sequence is graphical. Okay, so this is our first direction, and the second direction is that if the second or the new degree sequence is graphical, okay, then the original one is also graphical. So we have 2 statements to prove. So let's first consider the easier one, okay. So which direction is easier? From left to right or from right to left? Which one is easier? 所以这边有2个方向 ，OK， 你要证明是本来的是 graphical， 本来的如果找得到 graph， 新的就会也会有 graph， 这是第一个方向。第二个方向是新的如果是 graphical， 所以换句话说，新的 degree sequence， 如果找得到 graph， 那本来的一定也可以找得到 graph。我所谓的找得到 graph， 就是可以找到一个 graph 去满足那个 degree sequence， 就去 realize 那个degree sequence 的意思。所以大家觉得哪一个方向比较简单 ？From D prime to D， right? OK， 所以为什么？嗯哼。
就是第一块是已经有点被处理掉的状况，那还原回去本来就补一个点回去，基本上应该是
Yeah, so the basic idea is that if you have a graph that realizes D prime, then you have like a smaller graph, okay? And the difference between these two, D and D prime, is like 1 vertex, right? So if you have this smaller graph, then all you have to do is to add 1 vertex to the smaller graph and some edges, and then you're going to find a graph that realizes D. All right, so from smaller graph to a slightly larger graph is easier, okay? But the other direction is not that trivial, okay? But anyway, let's start with the easier one, okay? So if D prime is graphical, then D is graphical. Okay. So once again, this is we know that D prime, this 2, 3, 2, 2, 1, 0, we know that this one is graphical, okay? And we want to prove that using this assumption that D prime is graphical to show that D is graphical, okay? All right, so what is the definition of a graphical degree sequence. So what does it mean when I say that a degree sequence is graphical? Yeah, you can kind of draw the degree sequence as a graph, okay? So there's a graph called G prime. I can realize D prime, okay? Okay, so for example, let's try to construct a graph that realizes D prime. Okay, so I guess this one realizes D prime, okay? So the degree sequence, if we like sort the degree sequence in non-increasing order, then it will become 3, 2, 2, 2, 1, 0. So we got 1, 3 here, and we got 3 twos, and 1, 1, and 1, 0. So yes, so this one, 3, 2, 2, 2, 1, 0. This one realizes this D prime, okay? So now we want to use this graph to find a graph that realizes D, okay? So you have to use this graph as like the basis, and to add some edges, some vertex, and to realize D. So how to modify the graph to realize the original degree sequence D. All right, so in D prime, we already have 6 degrees. So actually, we don't have to add vertex, all right? So we already have 6 vertices. So all we have to do is to add edges. So how to add edges so that we can realize this D? So in this example, we can just add an edge between 0 and this one that has degree 2. Okay? And that's it. So this is a graph that realizes the original degree sequence D. Okay? So now it becomes 3, 3, 2, 2, 1, 1. Okay? Now what is so special about this degree 2 vertex? So it is like one of these degrees that are subtract by 1 from the original degree sequence. So we can see that there's a -1 here. Okay, so that's what we're looking for. Okay, we want to find the degrees that are like being modified, and then we're going to just add the original edges back to the graph. Okay. Okay, so I'm going to write down D prime again, okay? So these delta degrees are the ones that are being modified. Okay. Okay. Okay, so we're going to first find the vertex, like the one that has the smallest degree or degree 0. Okay. So in our previous example, this is Vn. Okay. We want to add some edges between Vn and some other vertices. Okay. So it's like we first try to locate the vertices that correspond to these degrees. Okay. And after we find this set of vertices, we just add edges between these vertices and this one. Okay. And that's it. Okay. So in our previous example, this is V1. Okay. Okay, so this is the graph, okay? So the new graph realizes D. OK， 所以这个 direction 是你有一个修改之后的 degree sequence。那不要忘记这个 degree sequence 怎么得到，就是那我们回一下。OK， 所以我们做的事情是，我们会把最小的 degree 的这个第二个 step， 我们会选这个最小 degree 的点，然后我们会帮它加一个边，加到那些 degree 最大的那些 vertex，OK， 然后接着我们就会去 update 这两个 degree， 所以我们做的事情有点像只是把这些 edge 再把它加回去，就结束 ，OK。所以我们刚刚的方向是，如果我们已经确定这个比较短的或比较小的这个 degree sequence， 它是 graphical， 所以我们就有一个 graph。那我们做的事情就是再加一个 edge 回去。那加哪一个 edge 呢？就是刚刚这个 degree 0， 就这个。那它一定会变 0， 因为我们就会满足它所有的 degree。OK， 所以它的 degree 不管是一开始是1还是多少，它一定会变0。然后我们会做的事情是在 step 3会加那些最大 degree 的那些把它连起来。OK， 那所以我们要做的事情就是把那些边有点像再加回去这样子。OK， 所以这个 proof 有问题吗 ？OK。 Okay, so then let's consider the second direction. Okay, that is the input degree sequence is graphical, and we want to prove that the new degree sequence is also graphical. Okay. So this is like we have a larger graph that realizes the original degree sequence, but then we want to have a smaller graph to realize the new degree sequence D prime. Okay. Okay, so this time because it is D, the original degree sequence is graphical, so we're going to call G the graph that realizes the input degree sequence D. Okay. Okay. So this graph realizes the original degree sequence D. Okay. And we want to create a graph to realize D prime based on this graph. Okay. So how to modify the graph to realize D prime?
From the graph, remove 3 to remove 1 to 1.
Okay, remove this one?
Yeah.
Oh, okay, okay.
And change 3 to 3 to 3 to anywhere that's on the right hand side.
So you mean like, remove this one and then?
3 to 3.
Okay, also remove this one, and then I guess I connect these two. Right, because you still have to realize the original degree sequence. So these two, that should still have degree 1. So you're going to eventually add some edges to these two. Okay, so.
One of these shouldn't have degrees. One of these two should be isolated. One of these two.
Right, that's because the final degree contains 0. Right, so how to get
Remove 1, 1 and remove 1, 3, 2.
this one?
No. Remove the 1. Just look at the black line and remove the 1, 1. 1, 1 pair. And remove
Right, it is already removed.
Yeah. And remove one of the 3, 2 pair.
3, 2. This one?
Yes. And make the one that is not isolated to the 2 we just removed.
Right, but I guess a simpler way of doing so is just to remove this one, because by removing this edge, you get 1 degree 0, and you get this degree 2. Okay, so. Okay, so okay, I'll draw a new graph. Okay. Okay. So both graphs realize the degree sequence 3, 3, 2, 2, 1, 1. Okay. But I think it's easier to start with the one on the right because so this degree sequence suggests that we should remove this smallest degree vertex and all its neighbors. Okay. So because if you look at D prime, the degrees that we are modifying is the one that have the largest degree, okay, and also the smallest degree. So it has like the effect that we remove all the neighbors of Dn, that is the one that has the smallest degree, and assume that all these neighbors are from the one that has the largest degrees. Okay. Okay, and indeed, this is the case for this graph because the one that has the smallest degree, this one, its neighbor is the one that has the highest degree. So if we just remove the edges instant to this smallest degree vertex, we get what we want. Okay, so we remove this one. Then this becomes 0, and this becomes 2. Okay. Okay, so the way we construct D prime, you can view this as you first find the smallest degree vertex, that is Dn. Ooh. Whoa. Okay, so these degrees originally have the largest degrees. Okay. okay? Because recall that D1 is greater than D2, which is greater than D3, and so on, okay? And this one is Dn originally, and this one has the smallest degree, okay? Okay, so from D to D prime, it has the effect that we remove the edges between the smallest degree vertex and the one that has the largest degrees. OK， 所以我们在从本来的 degree sequence 一直到 D prime 这个过程，马后炮来看的话，它基本上做的事情就是它会把那个最小的 degree 的 vertex， 假设你已经有一个 graph 可以 realize D 的话，还有点像是就是把那个最小 degree 的 vertex 的所有的边都移除 ，OK， 然后它会假设说这些边都是连接这个最小 degree 跟这些最大 degree 的点，所以把它移除之后，就会变成我们刚刚看到的这个样子 ，OK。所以这个右边这个 graph 做的事情很简单，它就是你要怎么从 D 变成 D prime， 你要怎么去找到一个可以 realize 这个 D prime 的这个 graph， 你就直接在 D 上面把那个最小 degree 的 vertex 的那个边删除，那这样子它就可以去 realize 这个 D prime，OK。Okay, so let's consider the easier case, okay? Because here we have two graphs, okay? The one on the right and the one on the left. We're going to consider the one on the left later, okay? So in the first case, we're going to assume that the smallest degree vertex, that is Vn, so this one has the smallest degree. We're going to assume that in this graph G, the smallest degree vertex is adjacent to the vertices with the largest degrees. Okay. And in this case, we just remove the edges between Vn and V1 up to V delta. And that's it. And then we can get a graph that realizes D prime, okay? Okay, because all these vertices, their degrees will be decreased by 1, okay? So then we can get D1 minus 1, D2 minus 1, and D delta minus 1, okay? And also we have this degree 0 because we have removed all the edges incident to Vn, okay? So now the degree of Vn becomes 0. Okay. All right, so this is like the easier case, okay, where the vertex with the smallest degree is adjacent to the ones that have the largest degrees, okay. But then we need to consider another case where the smallest degree vertex is not adjacent to those with the largest degrees. So then we have to modify the graph a little bit and then do a similar trick. Okay. All right. So let's first take a break. Okay. All right, okay, so that is case 1, and then we're going to consider case 2, okay? All right, so what is case 2? Case 2 is when Vn, that is the one that has the smallest degree in graph G, is not adjacent to some vertex in this set, okay? Is not adjacent to okay. Okay, so once again, when you see Vn, you're going to think that this one is the one that has the smallest degree, and this set are the set of vertices that have the largest or the most neighbors in the graph, okay? So I'm going to call this vertex U, okay? So let me draw a picture to visualize this case. So this is our Vn, and this is V1. Okay, so in case 1, all the vertices in V1 up to V delta are adjacent to Vn, okay? So in case 1, it's easy, we just remove all these edges. But in the second case, what happens is that we miss some of this edge here, okay? So we're going to assume that this vertex U is not adjacent to Vn. Okay? Right, so first of all, what is the degree of Vn in the original graph? 所以在本来的这个 graph G 里面 ，Vn 我刚刚说了 ，Vn 就是那个最小的 degree 的 vertex， 那个最小 degree 的 vertex， 它的 degree 会是 delta，OK？ Okay, so if Vn has delta neighbors, and some of, again, this set has delta vertices. So if one of these vertex is not adjacent to Vn, this means that Vn is adjacent to some of vertex in this set. Okay. Let's call this vertex x. Okay. So Vn must be adjacent to some vertex x in the set of vertices that have like the smaller degrees. Okay. So this one has like the largest degrees, and this one has like the smallest degrees in the graph. Okay. So all we want to do is to like restore this edge, because once we have this edge back in our graph, then we can just use the proof in case 1. We just remove all the edges between Vn and this set, and then we get the graph to realize D prime. Okay, so the goal here is to add this edge back to our graph, And so this means we have to remove this edge, okay? But then this will change the degree of x and u, because once we add this edge back, the degree of u is increased by 1, okay? So this graph no longer realizes the original degree sequence d. Similarly for x, if we remove this edge, then the degree of x will be decreased by 1. So once again, the degree of x, it changes, okay? So it no longer realizes the degrees, the original degree sequence. So we have to do more modification to the graph so that it can still realize the degree sequence d, but we have this edge and not this edge. Okay. 所以整理一下，就是我们现在的状况是，我们的在第二个 case 就是最小的 degree 的那个 vertex， 因为它其实不是连到所有这些 degree 最大的那 delta 的 vertex。这个 case 就是如果 v 最小 degree 那个 vertex 连到所有 degree 最大那个 vertex， 就是第一个 case。OK， 我们就很简单，我要怎么得到一个去 realize 那个 d prime 的 graph， 就是把所有 vn 到这个的 edge 全部都删掉。OK， 全部这边删掉，这些点 degree 都会是减一减一减一减一，然后这个变0，这个就是我们想要的。OK， 那现在的状况是，但是 u 呢，有一个 vertex u 它没有跟 vn 相邻，所以你把这边删掉之后，这个 u 它的 degree 不会减一。OK， 不会减一就不会是我们想要的。Alright， 所以我们现在要做的事情就是要想办法把这个 edge 可以加回去，然后把这个 edge 加回去，把这个 edge 删掉。OK。但是我刚刚说，你加了这个 edge，u 的 degree 就会变大，就会增加1，然后你减掉这个 edge，x 的 degree 就会减1，所以这样子的 graph 它就没有办法满足本来的那个 degree sequence d。OK， 所以我们会需要做更多事情，才可以让才可以找到那个新的 graph。OK， 所以有人可以看得出来说要怎么做吗？你讲。
因为我们想要让vn 的 degree 减1嘛
，vn degree 要变0，
然后那个跟前面大的某一条也减1嘛。
不，你可以不太正确，就是我们现在要做的事情是要让 vn 的 degree 从 delta 变成0。对。
因为我们先探讨说跟其中某一个点就好了，跟最前面的，比如说 v1 就好了。
v1OK， 然后。
那假设 vn 跟 v1 中间有边就直接移掉。
对。
如果没有边的话，那我们要找一条交错的一个那个路径，然后让它是有边没边，有边没边，然后最后头尾都是有边。然后我们把它翻转过来，是不是
？OK。
中间不变，然后头跟尾会减1。
可是你的那个尾巴就会减1啦，但我们不希望尾巴会减1，我们希望
我们也要把 vn 减1啊，我们希望 vn 跟 v1 同时减1。
不 ，vn 不是减1，vn 我们要把它全部拿掉，vn 就会是刚刚这个。
对，我们想要把它全部拿掉，但是因为它会跟 v1 到 v delta 做一次，
对。
所以呢，我们每一次 vn 都是减1。
OK， 了解。但是我说这个 path 的那个尾巴，它就会
这边跟这边都会减1，然后
可是那个尾巴就我们会不希望它改变 degree， 所以我猜你的意思是这样子。
v1 是在最尾巴，然后 a b c 在中间。
OK， 了解。我同意你，就是如果是可以找到这样子，然后所以这样事实上你还要控制它里面的 vertex 的个数。所以你说找到这样的 path， 然后 删掉这3个，然后补这2个。完全同意你。但是我现在想不到要怎么找到这样的 path。OK。
然后，所以我们假设 V1 它连出去的数字是 A， 就是它的 degree 是 A。
OK。所以 D1 等于 A。
然后那个，所以我们知道说，我可以画一下。
OK。
就是
没问题。你可以直接画在上面，对。你就直接画就可以。
直接画就可以。
对，它这个可以直接画上面。对。
所以我们假设说这边有一个点，然后它是 V1，然后它连了 A 条边出去。
啊哈。
然后这个点是 Vn， 然后它连了 B 条边出去，但是这个 B 应该是不重要。
你的 B 应该就是我们的 delta 嘛，因为我们刚刚有讲。OK。
然后，那我们知道说，我们如果中间有任何，就是这2个连出去的点中间有任2个点，中间没有边的话，我们就可以找到一个下面我想要找的路径。就是比如说这个点跟这个点中间没有路径，所以我这边就可以找一条扩增路径。
OK。没，这样我知道，我知道。OK。
然后所以这边是 A 嘛，那这边这个点的 degree 至少是 A 加1。
OK。Excellent。OK。Okay, I'll try to formalize your idea. Okay. All right, so first of all, I want to say that we have the same goal. Okay, the goal is to remove the try to add this edge back. Okay. No, but I think you still miss this edge, right? Because U or V1 and Vn, they are like the endpoints of the path, right? So, but you still have no. Oh, okay, and then
如果把头跟尾
再连起来。Oh, okay, okay. Right, so. So this Vn is the one that has the smallest degree, and currently it is adjacent to some vertex x. Okay, so x belongs to this set of vertices that have smaller degrees. Okay, and Vn is not adjacent to U. Okay, so our goal is to remove this one. So the goal is to remove Vn x, okay? And we're going to add Vn u, okay? And still, we cannot change the degree of x. Okay. So it's like we want this edge, okay, the edge between Vn and U, okay. We want this edge back, and we want to remove this edge, okay. Okay, so actually we cannot modify the degree of U either, okay. Okay, so here we have added this edge and removed this one, so we still have to add some edge to X and remove some edge from U. Okay. 所以你叫什么名字？陈义全。陈义璇。Okay. So Yixuan suggests that, yeah, that's if so here I draw the neighbors of X and neighbors of U. So Yixuan, okay. So Yixuan suggests that if we can find some neighbor of U that is okay. So Yixuan suggests that if we can find a neighbor of U that is not adjacent to X, right? Okay. So okay, so like this, so we do not have this edge, okay? And perhaps, let me do this, okay? And let's call this vertex Y, okay? So this vertex Y is a neighbor of U, but Y is not adjacent to X, okay? So then we're going to just add this edge and remove this edge. Am I right? Okay. So I'm going to add this one and remove this one. Okay. Okay, now let's compute all the degrees, okay? So for Vn, the degree is still delta, right? Because we remove one edge, but we add one edge back, so the degree is delta. So for X, we remove one of its edge, but we add one new edge from X to X. So the degree is not changed. Okay, and for Y, the degree is not changed because, again, we removed one and we add one. So not changed. Okay, and for U, we remove one and add one. Okay, so not changed. Okay, but we get what we want. So we get the effect that Vn, the one that has the smallest degree, is now adjacent to U, okay? The one that has like one of the largest degree vertices, okay? But now the question is, So what is so special about this y? And why can we assume that y and x are not adjacent? So how to find such a vertex x?
因为u 的 degree 是 d1，
Not necessarily d1, yeah. But it belongs to the one that it belongs to a set of vertices that have the largest degrees. Yeah.
and x 这样的话，如果它跟 u 连出去的所有点都有边的话，它会是 u 的 degree 加1。所以 x 的 degree 大于0是个矛盾。
Right. So, but what is x?
x 是一个比较小的。
Right, right. So the key here is that u has a large degree, yet x has a small degree. Okay? So it's like you have more neighbors than x does. So we can always find a neighbor of u, in this case y, okay, which is not adjacent to x. Okay? 所以这边的关键就是首先这个 u 跟 x 它们的关系是什么 ？OK， 所以这边最重要的关系就是我刚刚说 u 是什么 ？u 就是一个我们想要有 edge， 但是没有 edge 的 ，OK， 我们想要 Vn 跟哪一些人有 edge， 就那些 degree 很大的那些人 ，OK， 所以我们这个 u 就是其中这一个，然后很遗憾的我们现在没有跟它相连 ，OK， 然后我们的目标是要可以加回去。那 x 是什么 ？x 是那个错的 edge。就是我们不希望 Vn 跟这个 x 相邻，但是很遗憾，在这个 graph G 里面它跟它相邻，所以在这个 case 里面，这个 x 它不在这个 set， 所以就代表 x 它有比较小的 degree， 所以这边的关键就是 u 的 degree 会比 x 更大 ，OK？ OK， 所以既然 u， 那这边事实上你刚刚有一个点没有考虑到，就是相等的时候。
因为没有 x 会是因为它有一条边要连到 v，
对。
所以呢，如果它跟du 全部都连的话，它会是 du 加1，因为它多了一条边要连到 v。像这张图du 是4。
du 是4，对。
然后那 x 如果要跟所有的那个 u 相邻的点都连的话，它还会多一条，就是 x 连到 vn 的那条边，所以它是 du 加1。du 加1不会等于 du， 不会小于 du。
啊哈。Okay. Okay, so the degree of u is at least as large as the degree of x. Okay. And x is adjacent to Vn. And u is not adjacent to Vn in the original graph G. Okay.
两个都等号嘛，就 du 大于 dn。 因为你假设 u 和 bn 不相等，所以你 du 就跟他讲的一样，如果你的 x 会有等号成立的话，就代表它不能跟 bn 相等，因为它跟所有 u 的邻居都连起来，这是不合理的，是违反假设，是矛盾的，所以不可能会有等号情况，一定都是 du 大于 dx。等号是那个一开始那一排，那一排是大于等于，比如说32221，它222可以等于。
Okay. At least from this graph, okay, we cannot conclude that the degree of x must be strictly less than the degree of u. All we can say is that the degree of u is at least as large as the degree of x. Okay, so yeah, so it is possible that these two have the same degree. And it's from this graph, from this definition. Okay. Okay, so first, let's consider the case where the degree of u is strictly greater than the degree of x. So in this case, we can always find a vertex y that is adjacent to u, but not adjacent to x. Okay. So this case is that when u has more neighbors than x does. So we can always find a neighbor of u that is not a neighbor of x. Okay. And this is the vertex that we are looking for, because all we have to do next is to just add this edge and remove this edge and remove this edge. Okay. So after we find this vertex y, the things become easy, because we just remove this edge between Vn and x, and the edge between y and u, and add this edge between x and y, and v and u. Okay. Okay, so this is when u has more neighbors than x. So what happens if they have the same number of neighbors? Why?
When you go back to the last page, because du is greater or equal to dx,
Mm-hmm.
but x has to be adjacent to Vn, and Vn is not adjacent to u, which means we have to compare two numbers. One is du, one is dx minus 1. Because x is adjacent to Vn, right?
Right.
So we don't have to consider like du greater than dx is one of the case, and the other case du equals to dx. We don't have to consider that because we're comparing the number of du and dx minus 1. Because x has to be adjacent to Vn, which Vn is not adjacent to u.
I see.
So we don't have to consider these two cases.
I see. Right. So let me modify the graph. Sorry, the proof. Okay. I think I'm going to just put it this way. Yeah, the logic is just that if we have these three statements, then automatically we get this y.
Yes. To prove what it is.
Yeah. So I'm going to just write that once we have these three properties, then there's a vertex y such a blah, blah, blah. Okay? Yeah. All right, okay. So excellent. So let's go back to this example, okay, and see what is x and what is u and what is y, okay? All right, so this is Vn. Now, what is V1? So V1 is this guy, okay, or this guy, okay? That's okay. So both can be V1, okay, because they all have the largest degree, okay? So the goal is to make sure that Vn is adjacent to V1, okay? But in this example, you can see that they are not, okay? So Vn is not adjacent to V1. So according to our previous notation, we call this vertex U, okay? So in our previous graph, U is V1, okay? So this guy is U, and what is X? All right, so X is like the wrong neighbor, okay? The neighbor that we do not want to see, okay? So is this guy, okay? So we don't want to see an edge between Vn and a vertex of degree 1, okay? We want to make sure that this degree 1 vertex is adjacent to some vertex with degree 3, okay? So this one is no, not welcome, okay? So we're going to find the vertex y. So what is y? Y is such a vertex that is adjacent to u, but not adjacent to x. So adjacent to u, but not adjacent to x, okay? So this one can be y, this one can be y, and this one can also be y. Okay. So let's, for example, choose this y. Okay. And then we just remove this one. Okay. So let's see what. So remove v and x and yu. Okay, so remove these two, v and x, and the edge between yu. Okay, and then we add v and u and xy. Okay. Right, so after this modification, we still have a graph that realizes D, okay? Because the degree is still 3 here, and 2 here, and 2, 3, and 1 here, and 1 here. So we still realize the same degree sequence. More importantly now, this Vn, the one that has the smallest degree, now is adjacent to the highest degree vertex. So then it becomes the first case, okay, where Vn is adjacent to the vertices with the largest degrees, okay? Okay. So now the graph satisfies case 1. Okay, so we can just apply the proof for the first case, okay, to finish the proof. Okay. OK， 所以这个 proof 大家有问题吗？所以基本上，如果整理一下我们刚刚做的事情，我们事实上今天目前为止就有证2个东西。第一个是经过一个 round 之后，我们会有一个新的或比较小的 degree sequence D prime。那我们一开始做的是说，如果这个比较小的这个新的 degree sequence D prime， 它是 graphical， 那本来的它也会是 graphical，OK？ 那这个要做的事情比较简单，就是既然那个比较小的、比较新的 degree sequence 是 graphical， 你就有一个比较小的 graph， 那接下来你只需要去加一个 vertex， 或加一些 edge， 你就可以去 realize 本来的 degree sequence，OK？ 所以这个方向的证明比较简单。那第二个方向呢是，如果本来的是 graphical， 那新的也要是 graphical，OK？ 所以这个要做的事情是你要删掉一些边 ，OK？ 那在有一些状况删是比较容易，就是你想要删的那些边，刚好就是那个最小的 degree 的那个点，它刚好都连到最大 degree 的那一些点，那 delta 的最大 degree 的那些点。如果是这样的话，你就直接把这些边连接最小 degree 的点的那些边全部删掉，你就有 dn 减1、dn 减第2减1、第3减1、第4减1这样的你要的 degree sequence。那如果不是的话，我们刚刚做的事情是想办法去调整这个 graph， 让 Vn 可以确保说它跟所有最大 degree 的那些点是相连的。OK， 那要怎么调整呢？就是我们刚刚做的事情，就是首先你要找到你的目标，就是那些没有连起来的，但是应该要被连起来的 vertex。所以这些 vertex 它有很大的 degree， 但它没有跟 Vn 相邻。然后就代表另外一方面，这也代表说你的 Vn 是跟错误的跟某一个比较小的 degree 的 vertex 相邻。所以我们要做的事情就是删掉这个，把它加回去，然后删掉它 ，OK。然后刚刚感谢 我易选 ，OK， 易选提供的一个方法就是去找 path。我一开始你讲 path 有点吓到我 ，OK， 因为 path 可能会很长，对，但事实上这边事实上不用到 path，OK， 它只需要 u 的 neighbor 跟 x 这样的关系就可以了，对，所以就最后你讲的这个 proof 跟我心中想是差不多的 ，OK， 那所以这边的关键就是 u 的 degree 比 x 更大，所以你一定可以找到 u 的邻居某一个邻居 y， 它跟 x 是没有相邻的，所以你就可以利用这个，然后简单做一些调整，你就可以拿到你想要的。OK， 好，所以到这边有问题吗？有吗？Yeah. Which one? The algorithm. Okay. Right.
Pick the smallest degree. Because in your proof, it can be chosen by a random vertices. We just
Yeah.
have to follow that. You have to find D, which is the largest set.
Right.
You have to find the smallest.
Right. So the reason that I choose the smallest degree vertex is just for, I'll say, a more clean notation, right? Because say you pick the largest degree in the second step, then what is the new degree sequence? But now D1 becomes 0, and D2 minus 1, D3 minus 1, D delta minus 1, and D delta plus 1 minus 1. Right, so it depends, the new degree sequence depends on the vertex that you pick in the second step. And so in my opinion, if you choose the one that has the smallest degree, then D prime becomes more clean, right? So that's the only reason. So actually you can choose any vertex you want in the second step, okay? Right, oh, okay.
You can choose any vertex in the second stage.
Right.
How do we prove that?
Well, because in the whole proof, we actually do not use the property that this guy is the one that has the smallest degree. We didn't use that property. Yeah. So you can try it yourself. Say, suppose we remove the vertex, or we pick in the second step we pick the one that has the highest degree. And then you need to modify this D prime a little bit, because now D1 minus 1 becomes 0, right? And this guy may still be Dn rather than 0. So you need to modify this degree sequence a little bit. But the proof idea is they are just the same. Yeah, perhaps let's try, okay? So let's remove 3. So this becomes 0, and this becomes 2, 1, 1, 1, 1. Now this is D prime. Okay. So again, our goal is to construct a graph that can realize D prime. Okay. So now suppose we have this graph which realizes D. Okay. So we're going to just follow the same idea. So, but this time, sorry, this is 2, this is 3. Okay. So the idea is to remove, or in the second step, we choose the one that has the largest degree. And we assume that it is adjacent to all the other large degree vertices. So this time it is 3. Okay. So you can see now this graph just works fine, because indeed in this graph, this vertex is adjacent to the other 3 vertices with the largest degrees. So after we remove these edges, we really get this one. Okay, so after remove these 3 edges, we get degree 0, 1, 1, 2. Okay, so the degree sequence is just 2, 1, 1, 1, 1, which matches this D prime. Okay, but still, so this is like the case 1 for our previous proof. Okay, so we can also consider like this one. Suppose our original graph is this. Okay. So again, in the second step, we choose the one that has the largest degree. It is this 3 here. So in this case, you can see that if we just remove these edges into this vertex, then the degrees become two. Okay. So if we start from this graph, which realizes the original degree sequence D, and just remove the edges between the vertex with the highest degree and all its instant edges, like this 3, then we get this degree sequence. Okay, so this one does not match D prime. Okay, so for this graph G, again, we are going to just like apply the proof for case 2. Right? So we want to make sure that this guy is adjacent to the vertices with the highest degree. But you can see that 3 is not adjacent to this one. Okay? Because according to our idea, this 3 should be adjacent to these 3 vertices, because these 3 vertices, they have the largest degrees, 3, 2, 2. All right, so but 3 is not adjacent to this one. Instead, 3 is a neighbor of this one that only has degree 1. So if we use the notation for the proof for case 2, then this is like U, and this is like X. All right, so we want to make sure that this one is adjacent to U, but not adjacent to X. So we want to add this edge and remove this one. All right? And according to Yixuan's idea, we're going to find a vertex Y, which is a neighbor of this U, but not a neighbor of X. So for example, we can choose like this one. Right? So, yeah. Okay, and then we just remove this edge and add this edge. Okay, so yeah, so you can check. Okay, So the degree here is 2, 2, remove 1, add 1, so still 3, remove 1 and add 1, so still 1. Yeah, so you can check that this graph still realizes the original degree sequence. But it has the nice property that the vertex with the highest degree now is adjacent to all the other vertices with the highest degrees. So then we can just remove its edges to realize D prime. Right? So really the ideas are actually the same. So in the second step, you can really choose any vertex. OK。还有其他问题吗？ OK， 如果没有的话，我们就先下课。
你说你的 YouTube 名字是
TWKUO， 对 ，TWKUO，sorry， 对，然后1、2、3， 对。哦 ，OK， 没问题。
到底要怎么找出那个 delta， 就是低 delta 那个位置？它的定义不是
低 delta 的位置。
就定义不是，它会有前面那一些会扣减一减一。
啊，对对对对。
怎么找出来？就随便给一个图，到底要怎么找出来？对，因为到这边的时候才是减一的嘛，然后到这里的时候就没了嘛。
对。
对啊，那到底要怎么找出这个？感觉就
应该说，我觉得我还没有我不是很确定我有没有完全理解你的问题。但第一个我要问的是，你知道 delta 是什么吗？对，所以 delta 是什么？
那可能是我跟你还没有完全。
哦 ，OK， 好，所以没关系，所以关键是 delta 就是简单来讲就是我们在第二个 step
peak 的那个
的那一个点的 degree。
对。
嘿，所以譬如说我们前面在我刚刚的 example， 在这里，所以我们刚刚就是选最小的 degree 嘛，这个 vn， 那它那个时候它 delta 就是1，对，那如果是我们刚刚后面后面这边看到的，因为我们选的是这个嘛，这里我们就会说它的 delta 就会是3，所以简单讲 delta 就是你删掉的那一个点的 degree。
因为可是我有点忘记前面同学问的，就是他是问说就可不可以删这个最大的？
对，可以，我刚刚说的是可以。
所以也是可以。那这样子为什么要就是？所以到底定义而言，到底是要 pick 最小的点，还是就是 any？any
真的是 any。只是说，刚刚说的，如果你今天 pick 不是最小的，你今天 pick 比如说最大的，就是你在写这个 D prime 的时候，你写出来就会不太一样。对，因为譬如说你还是可以写，
还是 graphical。
对，还是一样会是 graphical。对。
所以甄选就，可是前面老师你不是说那个是 run？
OK， 那一个是差别是这样，那个的差别是我们每次在选的时候是选到，就第3个 step 帮他选邻居的时候是选那些 degree 最小的，差别是在这边。对，所以我这边应该我刚刚一开始写错位置了，这个应该是差的。
所以应该是通常会选最小。
你说第2个 step 还是第3个？第2个 step 我不会说通常要怎么选，就第2个 step 真的都可以，真的是都可以。那你只是要确保说你在 帮他选邻居的时候，你要选那些 degree 最大。对，对。哎
请你帮我签那个网络通讯概论的退户单。
哦 ，OK， 好。哦，你，好 ，OK。好。Okay, so so next we're going to consider the problem of finding not just a graph but a kinetic graph. Okay, so because you can see that, for example, in this degree sequence 3, 3, 2, 2, 1, 1. There are multiple graphs that can realize this degree sequence. And some of these graphs are disconnected, okay? But sometimes we want to have a connected graph, all right? So this time we want to have a connected graph to realize the degree sequence, okay? So there are the two questions that we can consider. So the first one is like more graph theoretical. That is, say you now have a graphical degree sequence, okay? And you want to just look at the degree sequence and tell whether this can be realized by a kinetic graph or not, okay? By just examining the degree sequence, right? So we want to have a very simple check to see whether this is possible to realize it by a kinetic graph. So this is like a graph theoretical problem. And then we have an algorithm design problem that is given a degree sequence. Try to find a kinetic graph to realize it, okay? So two types of questions, okay? But first I want to first define here the potentially kinetic degree sequence. So basically this means that this degree sequence can be realized by some kinetic graph, okay? Okay, so it is important to note that for the following discussion, we're going to assume the degree sequence is already graphical, because if it is not graphical, it certainly cannot be realized by a kinetic graph, okay? So if D can be realized by some kinetic graph, then D is called potentially connected. Okay. So I want to stress that if this degree sequence is potentially connected, we can still find some disconnected graph to realize it. Okay, so a potentially connected degree sequence does not imply that all graphs that realize D or all graphs that realize this degree sequence must be connected. No, okay, we can still have some disconnected graph to realize D. Okay, so here it is just some. Okay, not not all. Okay. Okay, so we have two questions. Okay, so the first one is we want to have a simple property check, right, by just examining this degree sequence and see whether it is potentially connected or not. Okay. Okay. So can you think of any simple check to see whether D is potentially connected? 接下来我们想要是去想一些简单的检查，去判断D 是不是 potentially connected. Okay. 或另外一个方向是，如果它是 potentially connected，它应该要满足什么样的条件？ Yeah, we already know that this is graphical. Yeah. How about 其他的？
Every vertex, their degree is bigger than 1, greater than 1.
Okay. Can we have degree 1?
Yes.
Yeah, okay, so at least 1. Okay. So if all degrees in D is at least 1, okay? So how about just this condition, okay? Is this statement correct? No, because, so can you give me some counterexamples? So, by this I mean that you have to design a graphical degree sequence such that all degrees are greater than 1, but you never realize it by a kinetic graph. Right, just a bunch of ones, then it's easy to see that, like just 4 ones, okay? If you have 4 ones, then you get, the graph must be just like 2 edges, okay? So it cannot be connected. So we must add more conditions. So we need 1 more condition. So what's the problem with this a bunch of ones?
Sum of all degree is larger than 2乘上1减。
Oh, okay, okay. So I think the intuition is that the total degree must be large enough because the total degree is proportional to the number of edges. Okay, in order to have a kinetic graph, you must have enough edges, right? So actually, the relationship between edges and total degrees is that twice the number of edges is the total degree. So total degree divided by 2 will be the number of edges. All right, so we want to make sure that the number of edges is large enough. All right, so to have a kinetic graph in a graph that has n vertexes, how many edges do you need at least? So you want to have a kinetic graph, and the graph has n vertices. N minus 1, okay? So n minus 1 is like the minimum requirement. So this means the total degree should be at least twice n minus 1, okay? So total degree of D must be at least 2 times n minus 1. Okay? All right, so next we're going to prove this. And so actually we can consider the other direction. So if D is a potentially connected degree sequence, then these 2 conditions must hold, right? Because if you can realize D by a kinetic graph, then since it is connected, we cannot have 0 degrees. In other words, we cannot have isolated vertices. And also, because it is connected, then it must, for example, have a spanning tree. And if it has a spanning tree, then the number of edges must be at least n minus 1, which means the total degree is at least twice n minus 1. So the other way around is easy, all right? So because once you have a kinetic graph, it is easy to, to have these 2 properties, okay? So we are not interested in the other direction. We are interested in this one, okay? So because this one also gives you a simple check. So once you know that a degree sequence is graphical, and you want to check whether this can be realized by a kinetic graph, you just check every degree, see whether they are greater than 1 or greater than, actually greater than 0, okay? And then you check the total degree, okay? So for example, in our previous 3, 3, 2, 2, 1, 1 example, first of all, no isolated vertices because all degrees are at least 1, all right? So check. And the second one, let's count the total degree. So the total degree is 12, all right? And here n is 6. So 2 times n minus 1 will be 10, and 12 is greater than 10. So this also passes the second check. So according to this result, 3, 3, 2, 2, 1, 1 is potentially connected, okay? But we have to prove it, okay? And before we prove it, let's consider the second type of questions, that is the algorithm design type of questions. So this time the input is a graphical degree sequence. D. And the output is, if possible, output a kinetic graph that realizes D. Okay. Or you can consider this question, okay? They are actually equivalent. The input is just a graph, and the output is a graph G prime such that first G prime is connected, and second G prime and G, they have the same degree sequence. Okay. So these two questions are actually the same, okay? Because once you have a graphical degree sequence D, you can use our previous algorithm to create a graph G that realizes D, okay? So you get this graph, okay? And then you just create a graph G prime such that the G prime, this graph G prime is connected and still have the same degree sequence, okay? All right, so as an example, we can consider this graph G, which is not connected, and want to find a graph G prime, which is connected and have the same degree sequence, okay? So we need an algorithm to do this. So how to do this? 所以我们现在要做的事情是想办法做一个 connected graph，OK？、所以你可以想象，你手上已经有一个 graph， 但它不是 connected，OK？、因为如果它已经是 connected， 那就不用做了 ，OK？ 所以这手上的这个一定就不是 connected。那我们要想办法做一个新的 graph， 当然我也希望基于这个本来的 graph，OK？、就基于这个本来的 graph， 然后想办法去对它做一些调整。 OK， 做一些改变，然后让它变成是 connected， 而且它的 degree sequence 是一样的，就一样是以这个例子而言的话，就是33221这样子。OK， 所以有什么想法吗？
原本的那个演算法不就可以那个了吗？就是如果你从最小的起手，因为它一定都是从，如果你从最小的 degree 开始走的话，
嗯哼，
那画出来的图如果不连通的话，会再把它没办法连通，因为它从最小开始，你都从最小去连最大，会有像这种情况，就是因为
我给你举例子。
OK，
假设今天是一个41111，然后222。
4，然后4个1，然后222。OK，
然后你如果照刚刚的跑法的话，你会把4个1都先连到4，
对，
然后再把3个2接成一个环。
打 OK，Yeah，Thank you。But this one can be realized by a connected graph, right?
可以，因为你可以把那个环打掉，然后连过去。
So, yeah, okay, yeah. Okay, so as another example, so this is a disconnect graph. I want to transform it so that it becomes a connected graph, but still have the same degree sequence.
因为它至少有 n 减一条边。
嗯哼。
所以如果它的连通分量大于1的话，表示它
连通分量是
就是假设它不连通的话，
啊哈，
那至少可以找到一个环。
OK。
然后从那个环取一条边，然后跟另外一个连通分量就是
component。
对 component。
嗯哼。
那个 component 中取一条边，然后跟这个取一条边，然后把它头尾都连起来变成一个环了之后，然后把它翻转就可以了。
嗯哼。Okay. So I think the high level idea is the following. Okay. First, find a cycle. Okay. And then we're going to remove, or we just after we find a cycle, we pick an edge called UV. Okay. All right, so this is an edge UV, and then we pick another edge in a different component. Call it XY. Okay, and then it's like we're going to merge these two components because we have a component here which has a cycle, and then we have another component which contains this XY. So visually, this is like so here we have a component, and this component has a cycle, and within the cycle we have this edge UV. Okay, and then we have another component, and within it we have this edge XY. And then we're going to just like merge these two components. So how to do this? We just remove these two edges and connect these two edges. Right. So remove UV and XY and add UX and VY. Right. So after this procedure, let's call it a round, okay? So after a round, we're going to reduce the number of components by 1, okay? So if still the graph is not connected, we'll just keep applying this procedure to find another cycle and another edge, XY, and merge these 2 components, okay? So that's the algorithm. But then we need to verify that this algorithm is always correct, okay? So, so first of all, how to find a cycle? Right, DFS and. So actually, there are many ways to find a cycle. You can use DFS or BFS. Anyway, actually, the idea is that once you have a spanning tree, and any edge that is not on this spanning tree will create a cycle. Okay. So first, find a spanning tree, and pick an edge that is not in the spanning tree. Then this edge will create a cycle. Okay. So we want to show that if we have these 2 conditions, then we can always find a cycle and another component so that we can run this algorithm. Okay.所以整理一下我们现在讲的 ，OK， 那我再讲我们接下来要证的东西 ，OK。所以刚刚的演算法其实蛮单纯的，其实就是想办法把，因为我们现在手上的是 disconnected graph， 就代表它有多个 components，OK。所以我们要做的事情就是想办法去 merge 这些合并这些 components， 然后一直合并一直合并，到最后它就变 connected。所以我们在合并的过程中必须要确保它的 degree sequence 是不变的。换句话说，就是每个点的 vertex 每个点的 degree 都是不变的。那我们要怎么做到这一点呢？所以刚刚易璇他的建议是，先想办法找到一个 cycle，OK？ 那找到 cycle 方法有很多种，那这个不重要，反正就找到一个 cycle， 然后想办法找到一个 cycle 之后，你就很容易可以在这个 cycle 上面找到一个边 UV，OK？ 然后接着你再去找，因为我们要合并 component 嘛，我们再去找另外一个 component， 然后在这个上面找一个 XY。然后我们接下来要做的事情就很简单，你就把这2个删掉 ，UV 跟 XY 删掉，然后再加这2个边 ，OK， 这样子一来，我刚刚没有特别讲，我现在再讲一下，我刚刚忘记了，就是这样子一来的话，它的每一个点的 degree 都没有变，因为每一个点 UV、XY 它们都是加一个边扣一个边 ，OK， 所以它们的 degree 都不会变，所以 degree sequence 一样是不变的。然后这2个就会很明显就会被合并在一起，为什么？因为这两个黑色的边就有点像是桥，把这2座岛连在一起。而且更重要的事情是，因为这边是一个 cycle， 所以这里 UV 就算你把它拿掉，这个岛它不会分裂 ，OK？ 所以因为你永远都可以用剩下的这些边把它们连在一起，所以这个做完之后就会合并成一个 component， 然后 degree 都不变。你可以再说一次吗？411111。
对，就是44个1，
4481，嘿，嘿，
这样子也是互相独立的，就不连通的2个 component，
嘿嘿。
找不到 cycle。
可是22还在不是吗
22就没有。
好，你说把这个22删掉，然后这边变4111这样吗 ？OK，OK，对，就是它就没有满足刚刚 total degree 要足够大。 如果是再加一个411的话，16嘛 ，total degree 是16。对，但是这边有9个不10个点，10个点的话total degree 刚刚的condition 应该是18，所以这会比较小。所以没错，这边有一个关键就是这个 cycle 不是随便一个 graph， 随便一个 degree sequence 都可以让你找得到，所以它一定要满足那个 total degree 要够大的那个 condition 才可以让你找得到。对 ，OK， OK， 所以还有其他问题吗？所以我们这边事实上有两个东西是不确定，第一个我们不确定有没有 cycle。然后第二个，我们不确定，这个看起来比较 trivial 一点，但就是有没有可能我在另外一个 component 找不到一个 edge？没错，所以这有一个我们很快就可以判断的事情，是因为每一个点的 degree 至少都是1 ，OK？ 所以每一个点至少都有一个邻居，所以如果你有多个 components， 那每一个 component 上面就一定都会有一个 edge， 所以不会说你找到一个 component 它上面只有一个 vertex， 不会。所以第二步一定永远都可以做得到。Okay. So next we're going to prove that if you have a disconnected graph and the total degree is large enough, then we can always find a cycle. Okay? Okay. Okay, so we're going to prove the following claim, which will prove this claim, okay? Because we have the algorithm already, so we only need to prove the existence of a cycle when the total degree is large enough and the graph is disconnected. So let G be a graph of, let's say, k components, and k is greater than 1. So this implies that G is a disconnected graph. Okay. So if the number of edges, recall that for this course, we always use m to denote the number of edges. Okay. If m is at least 2 times m minus 1, m is greater than m minus 1, or the total degree is at least twice the number of edges minus 1, the number of vertices minus 1, then there's a cycle. In G. Okay. Okay, so how to prove this? So here we have two assumptions about the graph. First being the graph is connected, the graph is not connected. And the second is it has at least n minus 1 edges. Okay. So given these two conditions, we have to prove that there's always a cycle.有想法吗？所以如果你手上的 graph 是 disconnected， 但是它的 edge 是够多了，是跟 spanning tree 的 edge 是一样多的，那我们一定可以找得到一个 cycle。如果这个 graph 是 connected， 就不一定 ，OK。所以比如说这个 graph 就是一个 tree， 就不会有 cycle，OK。所以这 graph 一定要是 disconnected。有什么想法吗？So let's consider a simpler question, okay? Okay, this time let's consider a kinetic graph, okay? So if the number of edges is at least n, then there must be a cycle, okay? I think this one is easier. Huh? So how to prove this? This time you have a kinetic graph, okay? And you have n edges instead of n minus 1, okay? So you have one extra edge.有想法吗？
可以先把那个图先想象成一个图是一条线，
一条线 ，OK。
但是前面要求它是两个 component， 就把一整个图拆成两部分。
嗯哼。
但是拆成两部分会少一条边，所以你需要在那两块其中一个地方加一条边，就一定会有 cycle。
我没有非常follow 你的 idea， 对，maybe 你可以再想一下，对。哎，
我知道他大概在讲什么。
哦，好。
下面那个的话，
嘿，
想象一个 path，
想那个 path，OK。
对，一条 path 要连起来的话，你至少要 n 减一条边。
对。
你如果 n 的话，就一定会有 cycle。
但如果不是 path 呢？
如果不是 path 的话，其实如果是 tree 还是什么的，应该也是 OK。
我讲别的。我们假设 n 个点一开始，我们用 disjoint set 的角度来看，如果一开始 n 个点全部都是只是一个集合嘛，所以它会有n 个集合，然后那我们每做一条边的时候，如果这条边的两个点如果在同一个 set 里面的话，它就会有环嘛。那所以我们如果把它全部变成一个 set 的话，最多只能有那个 n 减一条，只能做 n 减一次，所以在做最后一次的时候，它就会变成一个环。 它就已经
对，但是你这边没有用到它是 disconnected 的性质。你在下面这个你在讲下面这个，
如果现在是
OK，
n 大于等于 n 嘛，所以如果做 n 减1次的时候，它已经变成一个 set， 所以你在做最后第 n 条边的时候，它那一条边一定是另外形成一个环，因为它第 n 条边的地方会在同一个 set 里面。
那我知道你的意思，但是我觉得，没有那么 clean， 就是应该可以有更简单的说法，对。
或者是因为我们现在知道，是先假设它是 disconnected，
你在讲第一个还是这样上面 OK？
对，所以就是有分了两半，然后假设它就是假设是n 好了。
你的哪？
对，那这样我们最多就是假设它都是 spanning tree 的方式的话，这样它的边数应该就是各自的点再少，就是最多的情况。但这样子总和还是不够。我们至少再加一个边的情况下，不管是加在哪一边，就至少会有 cycle。
OK，所以你刚刚我想有一个隐含的 idea 没有讲，就是如果这些 component 上面都找不到 cycle， 那这些 component 就一定会是 tree， 对，因为第一个它是 connected。OK， 所以它一定会有一个 spanning tree， 但是你没有 cycle， 所以就代表它不会有任何一个多的 edge。OK， 所以这个跟这个事实上是一样的啦，就是等一下我用你的 idea 把那个 proof 写下来，但我还是回答一下这边，就是如果它是一个 connected graph， 那第一个它就一定会有 spanning tree， 那如果你有 spanning tree， 你就会至少有 m 减1个边，当然你现在要多了一个边，所以任何一个边再加上一个 spanning tree， 你就会产生一个 cycle。所以你就会有 cycle，OK， 好，那anyway， 我们回到你刚刚的 proof，OK， 所以我就等一下我就不用底下这个 claim 了 ，OK。So we're going to prove by contradiction. So that we're going to assume that every component does not have a cycle. Okay. Okay. And then we try to get some contradiction. So because every component doesn't have a cycle, this implies every component is a tree. Okay? So that that C1 up to CK be the components. And that, so here I need some notation, okay? So here Ni is the number of vertices in Ci, and Mi is the number of edges in Ci. Okay? So because every component is a tree, this implies the number of edges in every component equals the number of vertices minus 1. Okay? So say you have a tree and the tree has say 3 vertices, right? Then the number of edges in this tree must be 2. Okay, so yeah. And then we can just, now we want to find a contradiction. So we're going to consider the number of edges in the whole graph. So let's M. So we just sum up the number of edges in every component and we get the number of edges for the whole graph. So that's this, okay? Okay, and because every component is a tree, we have this. Okay, and we just take out this -1 from the summation, and since there are k of them, so we get -k. Okay. And here we just sum up all the number of verses in every component, so we get just n, which is the number of verses in the whole graph. So the number of edges in the whole graph is equal to m minus k. Right? So that's a contradiction, right? Because we assume the graph is disconnected, so k is greater than 1. So but we assume that m is at least n minus 1, so that's a contradiction. Okay. So because the graph is disconnected, so k is greater than 2 or equal to 2, all right? But we know that the number of edges is exactly m minus 1, so that's a contradiction. Okay. 有问题吗？对，所以整理一下，我们刚刚一开始讨论的是一个 graph theoretical 的问题，所以我们想要有一些简单的 check，OK， 去判断一个 graphical degree sequence 有没有可能被一个 kinetic graph realize。所以我们刚刚想的这两个，第一个是不能有，直接上来讲你不会有 isolated vertices， 所以换句话说 degree 一定至少要是1 ，OK， 然后第二个是它的 total degree 或者是 number of edges 应该要够多，才有办法变 connected graph。OK， 所以我们有这两个 condition， 所以这两个 condition 某种程度是我们直觉上得到的。那我们刚刚做的事情是去验证我们刚刚的直觉是正确的。那我们怎么去验证直觉是正确的？我们事实上我们就去想一个演算法的问题，我们去想给你一个 degree sequence， 你要怎么判断说它是不是 potentially connected？OK， 所以这个问题就让我们去想，如果我们手上有一个 graph， 那它很不幸的是 disconnected， 那我们要怎么样去对它做一些修改，让它有一样的 degree sequence， 但是它变成 connected？OK， 所以我们刚刚做的事情是，我们有一个演算法，然后我们去证明了，如果有刚刚那两个 condition， 第一个不会 isolated， 第二个 total degree 够大。那这个演算法就一定可以帮我们找到一个 kinetic graph， 所以就证明一开始那个 claim， 然后也证明这个演算法它在满足刚才那两个 claim 的情况下，那两个 condition 的情况下，它可以帮我们成功的转成 kinetic graph。OK， 然后这边的关键就是你要想办法去 merge components。OK， 所以你要 merge， 我们要做的事情就是要删掉一些边，然后连上一些边。 因为你的过程会删掉一些边，所以你必须要确保说你删掉之后，本来的 component 一样会是连起来。所以为了这个，我们就去找一个 cycle，OK？所以结论就是，只要你的 total degree 是够大的，那而且你是 disconnect graph， 你就一定可以找到 cycle。所以这个拿掉，你就一样不会断掉 ，OK？ 然后再做这些，有点像是去 swap 这些 edge， 我们就可以去 merge 这些 components。OK？ 好，所以到这边有问题吗？都没有 ？OK， 如果没有的话，我们就今天就上到这里。